Okay, good afternoon, everyone. Hope you guys had a good week. We're going to finish up our linear algebra review today, and then we're going to move on to our first machine learning unit. So where we left off was we were about to talk about eigenvalues and eigenvectors. So I think the best way to understand this concept is if you think about the matrix A as a system or a black box where it acts on a vector to produce another vector through matrix multiplication. So if we have okay, so what I'm saying in a picture would be like this. You have a vector v. To get A times V, you think about a black box, which is A. So when you think about such a system, generally speaking, when you put a vector into this black box, out comes a completely different vector, meaning it's going to be pointing in a different direction. It's going to have a different length. But there's a special set of vectors that when you put them through this black box, they come out pointing in exactly the same way as the input. And those things are the eigenvectors. Now the length of the eigenvector can change, but the direction stays the same. So that's expressed here. If you put vi through that black box A, you get out vi, but scaled by some number lambda I. And we call these vi's the eigenvectors, and we call the lambda i's the eigenvalues. And if you have an n by n matrix A, then there's up to n different eigenvectors, each one with its corresponding eigenvalue. Okay, so that's probably how you want to think about eigenvalues and eigenvectors. So this would be the equation we would use if we're thinking about a single eigenvector vi. But you could also imagine extending this equation by stacking v1 and then v2 and so on, and stacking all these different eigenvectors together. And you could call that matrix of horizontally stacked eigenvectors capital V. And now we're talking about A times V. Well, to get the right side, you would have that diagonal matrix of lambda 1 through lambda n times that same matrix of v1 through vn. And hopefully you can see why this works, because the first column of this thing we're talking about, which is like A times V1, that would be this times this, which is lambda 1 V1. And the second column would be, actually, I messed this up. Sorry about this. I swapped the ordering. I want it to be like this. I want to talk about rows. Okay, so it goes like this. So, so the first column, this guy here, would be this times this. So this times this, let me be explicit and put the zeros down there. This is a diagonal matrix. If you multiply this times this, you get lambda 1 v1 plus 0 times v2 plus 0 times v3 and so on. And so that's how you get this term lambda 1 v1. Now if you move over to the second column, that would be the second column, which would have a lambda 2 here, and this thing would multiply this, and you would get 0 times v1 plus lambda 2 times v2 plus 0 times v3 and so on, and you'd get lambda 2 v2 and so on. So after you do all that, you can see that in total, we can write all these eigenvector value things together like this, where v is stacking of the eigenvectors and lambda is this diagonal matrix over here. Okay. Any questions so far? Making sense? Okay. So there's a few properties of the eigenvalues we should talk about. The first one is that the eigenvalues can be complex valued, complex numbers. So all the quantities we deal with in this machine learning class are going to be real valued. For example, like we'll just think about real valued A vector, real valued A matrices, and so on. But it turns out that these eigenvalues can be complex even when A is a real valued matrix. Okay, the second thing is that the trace of A, if you remember that is the sum of the diagonal elements in A, ends up being the sum of the eigenvalues. And finally, the determinant of A, which was this kind of complicated volume thing, that ends up being the product of the eigenvalues. So these eigenvalues, tell you a lot of interesting things. Now, in the case that A is symmetric, a lot of nice things happen. So first of all the eigenvalues become real. And second of all, the eigenvector matrix becomes orthogonal. And if you remember with orthogonal matrices, one of the properties we have is that the inverse of V is just the transpose of V.
What's meant by symmetric?
Oh, symmetric matrix. Symmetric matrix is a matrix that is invariant to its transposition. So it's a matrix for which if you transpose it, you get the same thing. So when you look at it, the upper right quadrant and the lower left quadrant are mirror images. Okay. All right, so all these nice things happen when A is a symmetric matrix. And one of the consequences of that is if you come back to this equation and you say, how do I write A in terms of eigenvectors and eigenvalues in the general case, we could multiply both sides of this equation on the right by V inverse, assuming it exists. And then we'd get V lambda V inverse. So that's the general case. But as we said here in this symmetric A case, V is orthogonal. So actually this becomes V transpose. And then we get this nicer eigenvalue decomposition. It's basically a way of writing A in terms of a product of three things: eigenvector matrix, eigenvalue matrix, eigenvector matrix. And there's a nice interpretation of this in terms of, again, A as this black box. It's basically saying that if you multiply A by a vector on the right, that vector is first going to go through the V transpose operation, then a lambda operation, then a V operation. And remember that when you have an orthogonal V, that's just a rotation. So it means that any symmetric matrix can be thought of as a product of three things: a rotation, a scaling, because this lambda being a diagonal matrix, it just scales each of the elements somehow, and then a rotation, and it turns out because the transpose is the inverse, these are the opposite rotations. So it's like rotate, stretch, rotate back. Any symmetric matrix can be thought of as a composition of those operations. Okay, so this is something we'll see several points throughout the course. Any questions on symmetric case? Okay, and then just some terminology. When you have a symmetric A with positive eigenvalues, we call that a positive definite matrix. And when you have symmetric A with non-negative eigenvalues, we call that a positive semi-definite matrix. And some important properties are that if you take this positive definite matrix and you surround it by X transpose and X, and let's think about what that looks like. So X transpose is going to be a row vector. A is a matrix. X is a column vector. What is the shape of that thing that comes out of there? Is it a matrix? Is it a vector? Is it a scalar? It's a scalar, exactly. This scalar value is guaranteed to be positive when you have this positive definite symmetric matrix. Likewise, when you have this positive semi-definite symmetric matrix, this, we call this a quadratic form, is guaranteed to be non-negative. And that's no matter what X is. Okay. There's one more thing I forgot to talk about, which has to do with when the A matrix is invertible. We also call that when it's non-singular. This happens if and only if all the eigenvalues are non-zero.
So what's the difference between definite and semi-definite?
Here there is a, you see one is a strict equality and the other is non-strict. Yeah. And this kind of inversion thing, you can kind of see that here. If there's if one of these scalings is equal to 0, it's like you take an input vector, you rotate it, and then one of those rotated coordinates you just set to 0, and then you rotate it back. So now, because I've set that rotated coordinate to 0, there's no way I can ever tell you what it was. So that system has lost information about the input. I can never get it back. And in that sense, it's not invertible. Invertible means what you do, you can get back. So if you have this block diagram here, if A was invertible, that means from this, you could get back V. But if A throws away a crucial piece of information about V, then there's no way to get it back. That's what it means to be non-invertible. Okay, so that's, yes?
If A is non-symmetric and the eigenvalue equals 0, can it be inverted?
Generally, no, but it's a little bit harder to see it. Yeah. Okay, great. Any other questions? Excellent. Okay, and the last couple slides are just sort of what I call matrix vector gymnastics, is examples of some stuff that we'll see several times throughout the course, stuff that I'll put on the first exam that just puts together several of the concepts about matrices and vectors that we've seen. So in particular, what we want to do is, so let's just say that this B matrix has little bij as the ith row and jth column, and this C matrix has little zik as the ith row and kth column. So our objective is to write this summation without the sum and using the matrices. And this is something that we'll see an example of, I think, later today when we get into the machine learning. Okay, how do we even start? So what I would say to start is just maybe draw some pictures to try to visualize what's going on. So when you look at this, you might say, okay, that sounds kind of like a matrix multiply. It has a very similar form to a matrix multiply. But the devil is sort of in the details. There's a summing variable, which in this case is I, and then there's different subscript indices. So let's just start out maybe naively and write down and say, okay, maybe this is the matrix C, has to do with the matrix C times the matrix B, like a matrix multiply somehow. So let's go one step further and let's write down, using some arrows, what variables are along which dimensions. So in this case, I would be coming down this way for C, K would be going across the columns, B, we would have I coming down this way, and J across the columns. And right away you see that there's sort of a problem in terms of expressing this as a matrix multiplication because we have a mismatch in the indices. Like for matrix multiplication, we need this times this, plus this times this, and so on, which means we need the index we're using, this inner dimension index, must be the same for both matrices, right? You can see that's not the case here. And for example, one thing that could result from this is you might actually have a different number of entries across the columns of C and the rows of B. It might not be any valid matrix multiply. Okay, but we can actually fix this. What we want to do to make this look like a matrix multiply is we want to move this from the row index to the column index so that it matches this. So how do I do that? Transpose it, exactly. So if I instead say this is C transpose, then that means that I is going across this way and K is going across this way. And now we have I and I matching. And when you think about this operation, that's exactly what we would be doing in the matrix inverse. We'd be doing like first times first plus second times second. We'd be summing over I this way. And so we're maybe halfway done. The last thing to realize is that this quantity here is just a scalar, right? It's not a matrix, it's just a scalar. It's a sum of scalars, which is a scalar. But over here, we have a whole matrix. This is a matrix multiply two matrices, you get another matrix. So how do we get this from the land of matrices to this particular scalar? The key is these other indices, K and J. So here we can see that in this expression, K and J are fixed quantities. Someone told us what they are. There's some numbers. We're just being general. We don't know exactly which numbers they are. They could be any numbers, but there are two particular numbers. Whereas here, in this picture, K is actually spanning a whole range, and J is spanning a whole range. Right? So we don't want that here. We want to choose a very specific K and J. So to do that, what we do is we take this matrix multiply on the left, which is an entire matrix, and then we extract the kth row and the jth column. And that will give us this summation that we're looking for. Okay, so this is at least one way of solving this problem. We've written this using those two matrices without a sum. Yes?
What's the purpose of doing that? Like, if you're just specifying a K column and a J column, then aren't you missing a lot of the matrix then?
Well, in this expression, for whatever reason, that's what we're interested in. We're just interested in that particular K and J pair. That's just, we'll see examples of this later. Yes.
Is it the same if I extract the row vector and column vector first and just put them like one dot product?
There's definitely different ways to do this. Here, we're not directly using any vectors. We're using scalars and matrices. But yes, there's other versions of this that would involve vectors.
And it should be the same if I just extract them.
Yeah, so there's many, many different ways. Here we saw, like, if you have a matrix product,
Yes.
right? We can write it in many, many different ways. They're all equivalent. So in this particular case, we were just using one of these. Okay. Good. Any other questions? Okay, is this the only way to write it? Or can anybody see an alternative way of writing this?
Wouldn't it be the same if you transpose B?
Exactly. We could transpose things. So we could have, there's different ways to do it. Let's do the visual way. So we could have said, at the beginning, why don't I put B here and C here? And now, when you look at how B is formed, I is going down this way, J down that way, and then for C, I down the rows, and K down the columns. And you can see, once again, that there's a mismatch, that this is not matching that. But we can fix this problem by transposing B. And if I transpose B, then we have the I over here and the J over here. And we have the same thing again, where we have a matrix on the left, but we want to extract a particular entry from that matrix. We want that to use the jth row of B transpose because of this J on the B. So that would mean we're doing J, comma, K.
So it doesn't matter which side you have B?
These are two equivalent ways of expressing the same thing. Yeah. And in fact, you maybe could see that directly through a different relationship that we said okay, so you can see the main thing that's going on here is I've swapped the order. I've swapped rows and columns, right? And swapping rows and columns is the same thing as transposing a matrix. So it should be consistent with transposing this whole matrix. And it is, because if I take C transpose B and I transpose that whole matrix, what do I get?
B transpose.
Exactly. We transpose them individually, but we swap the order. So everything you can see is consistent. There's two different solutions to this problem, this one, and they're both equivalent. Okay, great. So everybody good with this little exercise? Okay, good. We'll do one more, and then we'll be done. So in this case, we just sort of have an extension. This is the quantity we saw on the previous page. But now we're going to square that quantity and then sum that over K. So when we're done, because we've summed over I and K, there should be no more I's, no more K's, but there should be a J somewhere. That expression should depend on J. Okay, once again, this is another scalar, and we're writing it in terms of the same two matrices. So maybe let's start out and just write, this is the thing we're interested in, sum over K. And by the way, if I don't write the limits as a summation, just assume that we're summing over all the entries. Sometimes it's a little bit tedious to write, all the limits. So I'm just, sum over K means all K. Sum over I means all I. Okay, so we have sum over all K times the quantity sum over all I, Cik, Bij squared. So the first thing you might notice is, well, this is a square, so I could expand the square, and I could plug in one of the expressions from the previous page. So maybe let me do C transpose B. C transpose B, and then the subscript was K, comma J. And since it's squared, let me repeat it. Okay. So hopefully everybody agrees with what I've done. And now, if you step back, you can say, oh, wait, this looks like another matrix multiply, except the first matrix is this matrix, or matrix with those entries, and the second matrix is this, and here's the summation. But again, it's not quite in the right form, because we want, if I'm summing over K, we want K to be going across this direction and down this direction. And on the right, it's happening. K is coming down the rows. But on the left, it's not happening. K is actually going down the rows, not across the columns. But as we saw on the previous page, we can fix this. We can replace the left with the equivalent expression. We get this. And now things are working out. We have K going down this way, and it's the summing variable. So everything's lined up. And that means we have a matrix multiply. So let me ask Zibang Li. Yeah. So what is the matrix multiply? How do I write this without the sum K? So this would be the first matrix. This would be the second matrix, right? So my first matrix is B transpose C. My second matrix is C transpose B. And now, this is exactly using the same ideas here. I don't want the entire matrix. I want the jth row and the jth column. So I take this matrix and I extract the jth row and the jth column. The reason I'm extracting the jth row is because here I'm looking at the jth row of this quantity, and the jth column, I'm extracting that because of the j there. And the matrix in the middle is a product B transpose times C transpose times B. So let me just maybe squeeze these together so it's clear that that's a single matrix. Okay, so what we've done in the end is we've written this double sum using those two matrices without any summations. Okay, so things like this will appear a lot over the semester, and our ability to kind of quickly see these things happening makes us understand like the deeper meaning of what else is going on in the machine learning. But we'll see some examples just later today. All right.
So the previous question with C transpose and B,
Yes.
that was the kth row and the jth column, correct?
Well, it was the kth row of C and the jth column of B. Actually, it depends. So here is actually the kth column of C and the jth column of B, right? But what we needed to do is we needed to transpose it. After we transposed it, then we looked at the kth row of C transpose and the jth column of B.
So whatever letters last in the scalar is what we want in our answer with no sum.
Well, okay, so when I ask the question, where should the J be? The J must relate to the B quantity. So if the B quantity is on the right, then J has to deal with the columns. If the B quantity is on the left, then J has to deal with the rows. So it really depends where B lands in the expression. Okay, great. Any other questions? Excellent. So let's move on to lecture 2, multiple linear regression. And let's just start with the example. So each one of these units is going to have a data set, an application, where we're going to be using that sort of throughout the lecture to illustrate both coding concepts and theoretical concepts and general machine learning concepts. So in this first or second unit, we have a data set that has to do with predicting automobile fuel efficiency in miles per gallon. And so that's the task. We're given data on aspects of different vehicles, like the number of cylinders in their engines, horsepower, weight, and so on. And we're also told what is the fuel efficiency for that particular car. And if we've seen a lot of examples of these things in fuel efficiency, maybe we can learn how to predict fuel efficiency from some new car just knowing this information. So that's sort of the high-level goal. The Python code is in this demo too, AutoMPG. You can find that on the GitHub page, and it's also, we'll see snippets of that code in this lecture. The data is coming from this OpenML repository, and we're going to use something called a pandas data frame to load our data. It's probably the most common way to load and view data for Python. It has a lot of nice tools and features, especially just for storing, viewing, and pre-processing data. So the main object in Pandas is called this data frame, and it basically has 3 main fields. It has the numerical values from the data set. It has some text labels that tell you the meaning of the different features. And then it has some other labels of the different examples in the data set, typically just numbers, let's say from 0 to however many examples you have. Or in time series data, maybe you have like data of stock price versus time. These other labels would tell you like the dates, like day 1, day 2, day 3, day 4, day 5, and then because of a weekend, you would skip over to, not 6 or 7, but 8, and so on and so on. So that's examples of what's in Pandas data frame. But Pandas as a library contains many other things, and so we'll see some examples of this. So let's just start with a visualization. This is a visualization of that Pandas data frame for this data set. And you can see in the middle, here are all the numbers. Here are those column labels. And here are the indices of the examples. So this is just like, for example, number 0, we have a car that has 8 cylinders. It has an engine with 307 inches of cubic inches displacement, 130 horsepower, 3,504 pounds, 0 to 60 acceleration of 12 seconds, built in 1970, and origin might be foreign, US, I'm not sure. But anyway, and you can see that that's one example, and then I have many other examples of vehicles in this database. In total, there's 397 examples. So separately from this object, which comes in when you load the data, you also get this AutoMPG target. And this, for each one of these rows, it gives you the miles per gallon of that vehicle, 18, 15, so on. So these are cars from between 1970 and 1982. So these mile per gallon are pretty bad by today's standard. But a few of them are okay, like this one has 44 miles per gallon. In any case, so that's like a visualization of this Pandas data frame. Now let's zoom out a bit, and let me tell you about a few other things if you've never used Python. So the first thing you need to do in Python is you basically need to load in the libraries that you're going to use. And typically you load them in and you give them an abbreviation so you don't have to type long words out. And the first library we're loading in is the Pandas library. And the standard abbreviation, the one we're using, is just PD. And then every time you reference something from that library, like a command, you're going to do PD dot the command name. We're also going to import the NumPy library, which is the standard numerical processing library in Python, and we're going to abbreviate that as NP. Now, in addition to importing entire libraries, you can also import just commands on their own if you don't want to import the whole library. So here from this scikit-learn datasets collection of functions, we're going to import fetch OpenML. And that is the command that goes to the OpenML website, retrieves the AutoMPG dataset, but it also, we can give it some other information like retrieve version number 1. There turns out to be different versions of the dataset on that website. And here we're saying when you download it or import it, format it as a Pandas data frame versus just like, it has other options. So this is what we get. Any questions so far? Okay. So let's talk a little bit about some of the notation. So all semester, we're going to use y to represent the variable that we are trying to predict. And there's many names for this variable. The ones I'm going to use most frequently are the target or the label, but there's other names like regressand, response variable, dependent variable. And the reason why it's important to know those is that there's a lot of other textbooks or web pages or whatever that you might encounter that are describing stuff that's totally familiar to you, but using different terms. And if you can't connect the term to what you know, you can't understand anything they're saying. So these are especially popular in the statistics literature, but these are more popular in machine learning, so we're going to focus on these for this course. So that's the thing we're trying to predict is y. Now the data we're using for prediction, we're going to call that x, and we're going to assume that we have possibly many different quantities that we're using to predict y. And so we're going to label those quantities as x1 through xd. And we're going to refer to these as features, but they also have other names like predictors, regressors, attributes, independent variables, and so on. Okay. So for us, like these would be our features, however many of those that we use. And we're going to use D to represent the number of features we're using for prediction. Well, and we'll be consistent all semester with this these names. There's a small typo. There should be a parenthesis here. If you consider pairs of examples of x and y, like here's an example of x and the corresponding y, you can think of those as a pair. And then imagine you have a collection of n of those pairs, like we have 398 of them. Here we're using the subscript I to index which pair. So this is, for I equals 0, this is y0, y1, y2, and so on. This is the vector of x, 0, vector of x, 1, and so on. And so this is our data set, the set of these pairs. Each one of these pairs we call a sample. N is going to be the number of samples.
So in our first lecture, you said that we'd also be working with object-oriented programming.
Yeah, we'll see some examples of that sprinkled throughout. I'll point them out when we see them. Okay. And one of the things that is really useful is just to try to visualize your data, because as humans, we're pretty sophisticated in terms of picking up relationships. And so just by maybe just visualizing things at the beginning, when you start working with data, you can notice whether there's some weird issues going on, or you get some insights about how, is this something I can predict, or is it just impossible? And so one of the ways you can do that is you can plot a scatter plot. A scatter plot is a plot of data points. So each one of these data points shows, for one sample, the horsepower, which is given by its horizontal coordinate, and its miles per gallon, which is its vertical coordinate. Okay, so I'm just looking at, for example, this, and plotting that as a single point. And then I'm taking the next pair and plotting that as another point. And now I've plotted here 398 points, and you can kind of see a trend in the data. You might ask the question, so would I be able to predict miles per gallon from horsepower alone? What do you think? Now, I can't predict it perfectly, right? But I can see a trend here. I can see a clear trend, higher horsepower, lower mile per gallon, and so on. So yes, I should be able to do something. And remember that we're not only using this feature, we're actually going to be using several features to do our predictions, so we should be even better than just using this alone. Okay, so that's a scatter plot. All right. So we would like to represent our data using matrices and vectors because it's much more concise. Question?
So in the previous slide,
Yeah.
so it needs to be so one feature to see the trend, but as we, like individuals,
Yeah.
but as we add more features, so it doesn't like affect the trend in a way that it will not be able to see trend.
It's more difficult to visualize it with a plot because as humans, so it's very easy to make these two-dimensional plots. You can try to plot in 3D. You can try to plot a point cloud, they call it, in 3D. But now what you see depends on which angle you're looking at it, right? So if you have the ability to rotate that point cloud like while you're looking at it, you might be able to get a sense for it. But if I just show you a static projection of it, it's hard, right? So that's why this scatter plot is typically a 2D sort of plot. You would actually need to plot a whole bunch of these. You could do horsepower versus miles per gallon, and separately you could do displacement. Separately you could do weight, and then you could look at all these, And you could even do, if you wanted horsepower versus displacement, you could compute a whole collection of these and maybe get some insights there. Any other questions? Okay. So so we want to pack things into vectors and matrices. And the way we're going to do it for our features is exactly like the way we saw in that pandas data frame. We have the features going across the columns, and we have the examples, or I'll call them samples, I, going down the rows. We'll typically denote the features by J and the samples by I. And so this, putting them all together in this matrix, we'll call that matrix capital X. Now sometimes I want to look at or talk about just one particular sample. So maybe I'm talking about the first sample. That would be this vector. Or maybe I want to talk about the ith example. That would be some row within this matrix. So I can extract that row, and I would notice that the first, the row index is always going to be I for the ith sample. And to give this a name, I would call it little x because it's a vector. But because it's a row vector, I would need to have that transpose on there too. Okay, so this would be the ith feature data. And I could also stack those rows on top of each other to get the full matrix X. For the targets, in this case, we just have one thing we're trying to predict, a simple scalar y, but we have many examples, n examples of it. So what I can do to be consistent with this is I could stack those samples or examples vertically, just like how I stack those vertically, into a vector y. And so now that I've done this, my data, I can think about it as a matrix X and a vector Y. That's my data set. It's much more concise, a little bit easier to visualize or read than this more complicated expression. Okay, everybody good with matrix vector notation here? Great. Okay, so let's start talking about how we're going to do our prediction. And we're going to start with the simplest possible thing we can do, and maybe even imagine. So again, just to review, we have a scalar target variable y. This is a real number. We have a vector of features. Each of those are real numbers, but in total, put d of them together, we have a d-dimensional vector. Here I'm putting the transpose there because remember, whenever we have an x vector, we're assuming it's a column. And if I didn't have the transpose there would be a clashed column and row. So I can either put a transpose here or here. I put it on the right. So our linear model, the way we're going to do the prediction goes like this. We're going to scale x1 by some number beta 1, which we'll have to choose. We're going to add to that beta 2 times x2, and so on, all the way down to beta d times xd. But this is not quite enough. We want to handle the possibility that there's some sort of offset in the data. Like if, maybe if all the x's are 0 in this case, y would necessarily be 0. But that might not be the way the data works out. So we're going to put in one more coefficient called beta 0, sometimes called the intercept term. And that's going to be our model. Now, this is called a linear model. But technically speaking, by the definition of linearity that I talked about the other day, which is like if you scale and sum at the input, that's the same thing as scaling and summing at the output, the presence of this kind of ruins that property. So technically speaking, this is called an affine linear model, which is like a linear model plus an offset. But everyone in machine learning calls this a linear model. They just kind of leave off that affine qualifier. So this is the model we're going to be using. And I want to point out the approximation sign. So this model is saying that the target is approximately equal to this linear combination of the features. But you never expect in practice for it to be exactly equal. There's always some sort of noise and modeling error in data. You never expect an equality. So the model just says that y is approximately this. Now, we want to have a name for the right side of this. This is the prediction we're making. And for that name, we're going to use y hat. So in this class, whenever there's a hat, that usually means this is an approximation or an estimation of some quantity. So in other words, we're saying that the prediction, y hat, is approximately equal to the truth y, at least if I can somehow set the betas in the proper way. Okay. So that's the linear model. Any questions on the linear model? Yeah.
The X are all scalars.
Yeah, all these x's are scalars. All these guys are scalars, at least in terms of the model. But remember that when I collect the data, I actually have many copies of each of these. So at that point, maybe you want to think about them as vectors or a matrix altogether. But at this point, when we just talk about like a single y, a single x, they're all scalars. Question?
I think I missed what you said. Like, what was the depth above the equal sign?
This is just an approximately equal to.
The,
Oh, here, yeah, good question. So this is a definition. So in some cases, I make distinctions between definitions and equalities. An equality is like some logical property that holds between two things. A definition is just like, I'm going to give something a name. There's no way you can argue with if I want to give something a name, right? You can argue with something being true or not true, but you can't argue with the definition. I'm just calling this, I'm going to call this thing, X, bold X.
So B1, B2, etc., that's the gradient for each feature?
Yeah, so these are the betas. These are the, what we call prediction coefficients. And these are things we're going to have to design in order to do the prediction. And you're exactly right that they are slopes, right? We'll see that in a moment. But yeah, these are the prediction coefficients. They're the things I need to design or to learn from the data. And notice how many of them there are. When we have D features, there's actually D plus 1. The 1 comes from that additional intercept term. And now you might say, like, how good is this model? One way to assess that is what's the difference between the prediction and the truth? And we can give a name to that. Epsilon will be the prediction error, or sometimes called the residual. Okay, is everybody good with the setup? So now the question is, okay, how do I set these beta? How do I come up with the best beta? Any thoughts on that? Yes.
You need to choose better somehow that this residual become minimal.
Yes, exactly. We want the residuals to be as small as possible. Now, the interesting thing is there's different ways to measure that smallness. And so there's actually kind of different criteria that we could come up with that say, like, how good are they? Like, maybe these betas are the best according to one criteria, and these betas are the best according to another criteria.
You can use the norms for that based on the norms.
A norm?
Based on the norm, it says, okay, you want the norm of this error.
Yes, yeah, that's exactly what we're going to do. We're going to define a criterion expression in terms of the norm. Is there another question? Yeah.
or you just do it least squares regression.
Yeah. Yeah, and in fact, we are going to do least squares regression, not because it's necessarily the best thing to do, but because it's one of the simplest things we can do. It's one of the things where we can do a lot of analysis and derivations relatively easily. Okay, so before we get all the way there, let's talk a little bit more about expressing these ideas again using vectors and matrices. So here we have our prediction. Now notice that this is the prediction for the ith data point. And then notice that I have on the right, I'm using features from the ith sample. So here I have, this is the first feature from the ith sample. This is the dth feature from the ith sample. And this is my prediction of the target yi from the ith sample. And what did I want to write here? Okay, so how can I write things on the right side in terms of a vector and vector there and a vector there? And what I'm going to do on the right is I'm going to put beta 0, beta 1, I'm going to stack those vertically. How do I form this so that it's consistent? So let me ask this to, is John Saw here?
Yeah, right here.
Okay. Yeah, how do I fill this in here?
Would that be Y1 to Y10?
So what we want to do is when we do this times this, we want to get this expression here.
Oh, it should be X.
Okay, so what goes in the first entry? That gets multiplied by beta 0 to get beta 0.
XI1.
For the second one, you're right. For the second one,
So it's 1.
exactly, 1 for the first one, which is sort of an exception. But then for the rest, you have like xi1, xi2, all the way to xid. Right? So here we've expressed this summation of terms in terms of an inner product between this and this. And based on our earlier notation, this portion, which is leaving out the 1, we call that the vector x sub I transpose. But in any case, this is what we want to use to write our prediction. And now furthermore, we want to stack all these predictions vertically over our data set from 1 to n. And we're going to call that a boldface y hat. And simultaneously, we will then stack all of these rows like this. You can see this is the first row all the way to the nth row. And then here we have the vector beta that we constructed above. And so here we're just giving names to all these things. We're going to call this augmented feature matrix, and it's augmented because it contains this new column of 1s that wasn't there back in the original feature matrix X. And now we can see that the whole purpose for including this column of 1s is to facilitate this multiplication with beta 0. Okay, so now that I have these quantities defined, I can write the y hat vector very compactly. So let me ask, is Ji Yuan Chen here? Yeah. So how do I write this in terms of these quantities?
I think it would be like beta times A.
Okay, let's think about this. If I did beta times A, let's think about how the dimensions work out. This is a column vector, and this is a matrix. That doesn't work. Yeah, exactly. A times beta. This is an example where the order really does matter. You write it one way, it's just invalid, and the other way is exactly what we want. Okay, so this is our prediction. Our prediction is simply A times beta. Now, this is what I'm going to use to train my model. But once it's finished training, and I want to apply that model, someone is going to give me a new feature vector, which I'll call x, that I've never seen before. It's not part of my training. Sometimes we call it a test vector. And I actually don't even know the true target. That's my goal. That's why I train this model. I want to try to figure out what is the y that corresponds to this new x. And the estimate that I come up with, I can create that using my beta vector once I've figured out what that beta vector is. Does anybody see how I can write something here times beta that involves x to get me what's approximately the target y that corresponds to x? How do I fill in this part?
It would be one, like a row vector, but 1 and then x transpose.
Okay, this is just a scalar 1, and then you're right, now there's a vector x transpose. So this scalar 1 is going to multiply the beta naught, which is the first term here, and then this x transpose will do the inner product with the rest of the beta terms, and those are both scalars. They'll sum together to give you this scalar y hat. Okay, great. So any questions on what we've done here? So we're sort of putting our pieces together. So let me just do one more slide. So this is the model that we have established. This is how we're going to do our least squares fit. Our objective is to choose the different betas that somehow are a good fit to our model. And there's many ways to do this, but we're going to find the beta that minimize the sum of the squared errors. or in other words, the sum of those residuals that we defined earlier, epsilon I. Our objective is to make yi and y hat I as close as possible, but we have to consider that we have many i's. So here we're just going to sum them or treat them all equally. And the way to visualize what we're doing is through this regression plane. So this regression plane, so what I'm plotting here is I have a feature x1 along one coordinate axis, x2 along the other. And this plane, this is my y hat as a function of x1 and x2. And so you can see, okay, if I set x1 and x2 to 0, then what happens with my y hat, if all my x's are 0, y hat is beta 0, right? So beta 0 would be the height that this plane crosses the horizontal, vertical axis at the origin. We know that as the intercept. So this is called the intercept coefficient. And then meanwhile, these other betas tell us the slope of the plane if I look in a different direction. So if I look along this coordinate axis, I might notice the plane has a certain slope. That would be beta 1. If I look along this axis, I might see a different slope. That would be beta 2. Rise over run. And at the end of the day, by changing all those numbers, in this case, beta 0, beta 1, and beta 2, I can shift that plane around. I can move it up and down. I can tilt it different ways. And I want to tilt it so that the difference between y hat, which is the location on the plane, and these black dots or gray dots, those are the data values, I want to make that as small as possible in some squared error. So I want to look at all the squares of those lines, sum all those squares together and minimize that. So that's what we're going to do. We're out of time for today, but we'll get back to this on Monday. Have a great weekend. See you guys then.